Hello everyone, in this video we're going to talk about trees and minimum cost spanning trees. More specifically, we're going to learn how to classify graphs as trees for us, rooted trees and spanning trees, and we're going to learn how to construct spanning tree from connected graphs. Also, we're going to apply an algorithm called cross-goals algorithm to find minimum cost spanning trees. Why do we need to learn trees? So tree was used as long ago as 1857 when the English mathematician called Arthur Cayley used them to count certain type of chemical compounds. And since then, tree has been employed to solve problems in a wide variety of disciplines. And tree of course is particularly useful in computer science where they are employed in a wide range of algorithms. For instance, tree are used to construct efficient algorithms for locating items in a list. Tree can be used in algorithms that construct efficient codes, saving costs in data transmissions and storage. Trees can also be used to study games such as checkers and chess and can help determine winning strategies for playing these games. And thus, knowing the concept of trees are very useful in computer science. Now, the first definitions I want to give you is the definitions of a tree. So a tree is a connected graph with no cycles. And now back to the question is, what is the connected graph? So a connected graph is a graph where every vertex can be reached from every other vertex. Let's consider the following example. So I have this 4 different graphs, and I'm going to name them graph G1, this is graph G2, this is graph G3, and this is graph G4. So graph G1 and G2 are trees, since they both are connected graphs with no cycles. So I could be able to recognize that because I followed the definitions of a tree. Again, a tree is the connected graph with no cycles. So for this 2 graphs, so G1 and G2 are trees because they are connected graphs with no cycles. So G3 is not a tree even though it's a connected graph because there's a cycle inside this graph. So a cycle you can form is going to be A, B, E, D, and then from D you go back to A, so that's the cycle. You can form order cycle inside this graph as well, right? But overall, it's not going to be a tree. So G3 is not a tree since it has a cycle. And the cycle that we form is A, B, E, D, A. Now G4 is not a tree because it's not a connected graph. So how can I know it's not a connected graph? By the definition of connected graph is the graph where every vertex can be reached from every other vertex. So here you can see you have an edge connecting A and F, and that's it. There's no connection between A and D. There's no connection between F and C. That means that there is no path for you to go from, let's say, A to D, or there's no path for you to go from A to C. Similarly, there's no path going from F to C, or F to D, or F to B, or F to E for that matter. Because this graph is not connected, therefore it is not a tree. So G4 is not a tree since it is not a connected graph. So you know about connected graphs, you know about definitions of a tree. Now, if you have multiple trees and they do not connected to one another, then we have something called a forest. So a forest is a graph containing no cycles. And I want to draw a remark here is that a connected forest is a tree. The second remark is that if you remove any edge from a tree, then the graph becomes a forest. So if you remove any edge from a tree, then it becomes a forest. So here's an example of a forest. So this is an example of a forest. You have 3 different trees here, and together they form a forest. Right? Now, if you want to connect these 2 vertices together using an edge, then this whole thing here is called a tree. Now from here you connect between these two vertices, and then the whole graph you see on the screen right now is a tree. Now, if you remove these two edges, then you go back to a forest. Okay. Now, the next definitions I want to cover is called the rooted tree. So a rooted tree is a tree in which one vertex has been designated as the root and every edge is directed away from the root. Consider the following example. You have this tree, and this is called a rooted tree. So from this rooted tree, I can form two different trees with two different roots. I'm going to form a rooted tree rooted at A. So the tree with root A. So I'm going to start with A here. I'm going to form a tree with a root A. So A is going to be on top, and the edges are going to be directed away from the root. So the edges that I have is going to be the edges connect A to D, the edges connected A to B, and the edge connected A to C. So this is what I have. So this is B, this is C, and this is D. And for B, you have two edges going away from that, connecting B to F and B to G. From C, you have an edge going away from that, connecting C and E. And for D, there's no other connection, so you can stop right there. So that's one example. In this case, is the tree with root A. Now you can form another tree with root C if you want to. And that means that you're going to start with C here. And all the edges going to directed away from C. And there are two edges directed away from C. That is, one connects C with A and one connects C with E. For A, you have one edge going to B and one edge going to D. From B, you have one edge going to F and one edge going to G. So I have another tree, but in this case with root C. Now, what about subtrees? If A is a vertex in the tree, then the subtree with root A is the part of the tree containing A, all the vertices below A, and the edges between them. So that's going to be the definition of a subtree. And all of this requirement right here is called the descendant of A. It's very similar to definitions of a family tree. So in this case, all the information here is going to be descendants of A, and A in this case is going to be the ancestor of all the part below it. So A is going to be the ancestor of B, F, G, and all the vertices below it. And you can see B, F, G, and all the vertices below A is going to be the descendants of A. So there are multiple subtree in a tree. You can have that this part of the big tree is going to be the subtree. So the subtree is going to can be, this is B, C, D, and E. So this is subtree with root B. Or you can have a subtree of this part right here, or you can have a subtree of this. We can try, this is J, and this is L, this is M, and this is a subtree with root J. Toward the end of the tree, you can see that D, E, F, I, K, L, M, they all have something in common, that is there's no other connections going from those vertices. Those vertices are called the no-child vertices. So you have no-child vertices, or you can call them nodes. They include D, E, F, I, K, L, M. And because they have no child vertices, the terminology you can use is called leaves. So all of this can be called leaves. Now we're going to cover more definitions. And the next definition is called spanning trees. And we need to know spanning tree because eventually we're going to do minimum cost spanning trees analysis. So what is a spanning tree? So for a given graph G, a spanning tree of G is a tree which has all the same vertices of G and some or possibly all of the edges of G. So a spanning tree of G is a tree that has all the same vertices of G and some or possibly all of the edges of G. Alright, so given this symbol graph right here, so this is the symbol graph, and I call this G. Now I want to find the spanning tree of this symbol graph. So what do I do? The first thing first you have to keep in mind is that you need to keep all the vertices of G. So in the next graph, as you can see, you include all the vertices of G. The next requirement is that some or possibly all of the edges of G have to be included as well in the spanning tree. But keep in mind the definition of tree is that it has to be a connected graph and there should be no cycle. Alright, so we need to avoid all the cycles. How to avoid all the cycles? You have to remove some edges to avoid cycles. So to arrive at the first graph, what you need to do is that you need to remove the edges connecting the vertices A and E. You remove the connections between E and F. You remove the connection between C and G. Then you have a spanning tree of the graph G. So in this case, this is a spanning tree of G. And what we did is that we removed the following edges. We removed the edge AE, we removed the edge EF, and we removed the edge CG. And of course, there can be multiple answers to this one question of finding the spanning tree of the symbol graph G. Another possibility for an answer is that I'm going to remove different edges so I can form the spanning tree. But keep in mind again that the spanning tree needs to have all the same vertices of G. And some of the edges, some or possibly all of the edges of G has to be included in the spanning tree as well. So in this case, what I did is that I removed the edge connecting A and B, I removed the edge connecting C and F, and I removed the edge connecting E and G. So this is also a spanning tree of G, but in this case I remove the edges AB, CF, and EG. Now for the last graph, this is also a spanning tree of G. What I did is that I removed the following edges. So I remove A and E, I remove E and G, and I remove F and G to avoid any cycles. But still, you have to keep track with the idea that a tree is a connected graph with no cycles. So what I did is that I removed the edges AE, FG, and EG. The next definition is the weighted graph. So a weighted graph is a graph with numbers assigned to its edges. So here I have two different examples for weighted graphs. So for the first one is a weighted graph showing the distance between cities. Now for the second graph, this is a weighted graph showing the lowest airfares going from one city to another. So a weighted graph showing the lowest airfare going from one city to another. So the next definition is minimum cost spanning trees. A minimum cost spanning tree or a minimum spanning tree in a connected weighted graph is a spanning tree that has the smallest possible sum of weights of its edges. And how could you possibly find something like that? You're going to follow certain algorithms. In this case, I want to introduce to you an algorithm called cross-call algorithm to help you find the minimum cost spanning trees. So given a graph G, and you want to find a spanning tree that minimizes total cost, what you do is that you first choose the lowest cost edge in the whole graph. Now, if you see there are multiple of lowest cost edges, then you can choose whichever edge you want. If there are more than one, choose whichever you want. Now moving on to step 2, of the remaining edges, choose the next cheapest edge. So of the remaining edges, choose the next cheapest edge, provided that it does not form a cycle with the spanning tree you built so far. So provided that it does not form a cycle with the spanning trees you built so far. If it does, then leave it and move on to the next cheapest edge. And move on to the next cheapest edge. And for step 3, the final step, repeat step 2 until you consider all the vertices of G. Now repeat step 2 until you consider all the vertices of G. And then after consider all the vertices of G, whatever you have is the minimum cost spanning tree. So this spanning tree is guaranteed to have the lowest cost. This spanning tree is guaranteed to have the lowest cost. All right, so I'm going to give you 2 examples. The first example is kind of a generic type of example, and the second example is going to go back to the connected weighted graph where you have the airfares going from one city to another. So in example 4, I want to find the minimum cost spanning tree of the given weighted graph, and after that I want to know what is the total cost of the tree. All right. So I'm going to follow the algorithm. So the first step is choose the lowest cost edge. And if there are more than one, choose whichever edge you want. So I can see here that the lowest edge is going to be 2 here, 2 here, and 2 here. So I'm going to start out with the edge connecting A and E. So I have A here, I have E here, and this is the edge with the weight 2. The next cheapest edge is going to be the one connecting C and D. So I'm going to start with that. The next one is F and G. I'm going to do that. So these 2 edges have the weight of 2. Now the next number is going to be 3. So I see there's 3 here, there's 3 here, and there's 3 here. So the edge connects C and F is going to have 3. So put 3, C and F here, and the weight is 3. Now, I'm not going to consider the connection between F and D, because if I do, connecting F and D, then I form a cycle, which I do not want to do. So I don't consider it, and I just ignore that, move on to another edge. Now, the edge connecting G and I, I'm going to consider. So this is I here, and I'm going to connect G and I, and the weight is 3. The next cheapest weight is going to be 4. So 4, 4, 4 here, and 4 here as well. Now I'm going to choose to use the connection between E and C. And the weight is 4. I'm not going to consider the edge connecting E and F, because if I do, I'm going to form a cycle in the spanning tree, and I don't want to do that. This is one of the possible solutions to this very problem. You can choose to go with the connections between E and F and leave the connections between E and C. In this case, I choose to work with the connection between E and C and don't work with the connections between E and F. So again, there's multiple solutions to this problem. Now moving on to the connection between H and G and the connection between H and I. They are both weighted 4. So I have H here, and I'm going to connect H with G, and the weight is 4, and I'm going to ignore the connection between H and I because I don't want to form a cycle. Now we consider most of the vertices in the graph except B. So I'm gonna eventually can see the B. The next cheapest weight going to be 5. So 5 here, 5 here. I'm not going to consider the edge connecting A and C because they're going to form a cycle in the graph, so I don't want to do that. But I still need the connection between A and B, so that is going to be the edge that I use. Now you still have the edge with the weight 7 and the edge with the weight 9. The problem with that is if you consider those edges, now make the connection between B and D, you form a cycle, so you ignore that. If you make the connection between D and G, you form a cycle, so you're going to ignore that as well. So what you see on the screen now is the minimum cost spanning tree of the given weighted graph. Now at this point, I want to do the calculation of the total cost of this spanning tree. So the total cost is going to be equal to 2 plus 5 plus 4 plus 3 plus 2 plus 2 plus 4 plus 3, and it's going to be equal to 25. So I just basically add all the numbers together, or add all the weights together. Now moving on to the last example, I want to find a route or a spanning tree with the least total airfare that visit each of the city in this graph, where the weight on an edge is the least price available for a flight between two cities. And of course, at the end, you want to know what is the total cost of tree. Now I'm going to look for the lowest airfare in the entire graph, and I see that there's $39 going from San Francisco to Los Angeles. There's $39 going from Boston to New York, and I'm going to start from there. So I'm going to start with San Francisco, going to LA. So this is LA. This is the connections, and the weight is going to be $39, which is going to write 39. Now move on to the next cheapest edge, that is going from Boston to New York. And this is also going to be $39. Now the next one is going to be $59, and I see that that's going to be the airfare going from Chicago to New York and vice versa. And I include that here. And there should be connections going from Chicago to New York. And it's going to be $59 for the weight. Now the next cheapest value is going to be $69. I have here of going from Atlanta to Miami, and going from Denver to Chicago, and vice versa. So I have Denver here, and I have Atlanta, and here is Miami. So the connections going from Denver to Chicago is going to be $69. The connections going from Atlanta to Miami is also going to be $69. The next cheapest airfare is going to be $79. So it's going to be the connection between Chicago and Boston, as well as the connection between Atlanta and New York. So Atlanta and New York is going to be $79. And I'm going to ignore the connection between Chicago and Boston, because if I do, I'm going to form a cycle, and I don't want to do that. And the next cheapest airfare is going to be $89, which is the one going from San Francisco to Denver, and the one going from Los Angeles to Denver. So you have to choose either one, because you cannot choose both. If you choose both, you form a cycle. So you can choose the one going from San Francisco to Denver. Again, you don't want to do this, right? Make the connection between LA and Denver, because in this case you form a cycle. Then the next cheapest one is going to be $99. So for this $99 going from San Francisco to Chicago, you don't want to do that because you're going to form a cycle. The one connecting Chicago and Atlanta, you're also going to form a cycle. You don't want to do that. And the one from New York to Miami, you're going to form a cycle, so you don't want to do that. You ignore that, and you ignore those connections. Then the next one should be 129 here, and they're both going to form cycle if you consider them in this spanning tree. So therefore, you ignore the connections that lead to $129. And what you see on the screen is the minimum cost spent in trees, with the condition is that we want to visit each of the city in this graph. And at the end, you want to calculate the total cost of this tree. And is equal to 39 plus 89 plus 69 plus 59 plus 39 plus 79 and plus 69. And the answer is going to be $443.